Good morning, everyone. Today we're doing Unit 2, Lesson 4, Comparing Polynomial Functions. So in this lesson, we're going to compare and look at the number of zeros a polynomial has. And we're going to need to use a graphing calculator like Desmos to graph the functions. But some of these we should be able to graph just because we know how to graph these types of functions. So let's start by looking at some linear relations. So in this linear relation, we have a y-intercept of 4, and we have a slope of -2. Okay, so I'm going to start at my y-intercept, which is at 4. 1, 2, 3, 4. And our slope tells us that we're going to go down 2 over 1. All right, we have a -2, 1. So down 2 over 1, down 2 over 1, down 2 over 1. Okay, and then I'm just gonna draw a straight line. I'm gonna try to draw a straight line through those points. And if we wanted to count how many zeros we have, we can see, well, how many times does it cross my x-axis? And it just crosses that one time. So that's our 0 or x-intercept. And it only crosses our x-intercept one time, so we have 1, 0. If we look at the next one, y equals 5, well, remember that that means that whatever my x value is, my y value is always 5. So x could be 10, my y value is 5. X could be a -8, my y value is 5. So what a y equals equation really does is it just is a horizontal line through that point on our y-axis. Okay, in this case, you can see it never crosses the x-axis, so it has 0 zeros, no zeros at all. All right. Something else I want to point out about these linear relations is I want you to notice how many turning points there are. So, number of turning points. So what I mean by that is if we're looking at the graph, is there a point where the graph is increasing, and then it changes directions and it starts decreasing, or vice versa? The graph is decreasing, and then all of a sudden it changes directions and starts increasing. So if we look at these lines, this first one is just decreasing. It never changes its direction. It never has a turning point. And my horizontal line is the same. My horizontal line is just horizontal. It's not moving up or down, but it certainly never changes directions. So the number of turning points for our linear relationship is 0. Let's look at our quadratic relationships. So we're going to use a table of values for this first one because it's not going to factor, but the next one might factor. So let's set up a table of values. And just because I know what the graph looks like, we're going to use x values between -3 to +1. Okay, so if I subbed a -3 in there, we will just sub it in over here so we can see what that's going to equal. So we'll have a -3 squared minus 2 times -3 minus 3. So a -3 squared is 9, and it's a -9. And we have a -2 times -3 is a +6 minus 3. Okay, so if we calculate -9 plus 6 is a -3. -3 minus 3 is a -6. So I get a -6 there. Go ahead and pause the video and finish filling out that table of values. So there's the rest of the table of values, and then I plotted the points on the graph. So we can see here that, again, this graph doesn't cross the x-axis, so I have no x-intercepts or no zeros. So I have 0, 0. Something else to notice that we would have talked about in the last note is that we have a function here that is negative because my coefficient is negative. My leading coefficient is negative. And it's to a degree of 2, so it's even. So that tells us if we have a negative even polynomial that our endpoints are pointing down, which if we look at our graph, we can see that is true. We have a quadratic that's pointing down. So let's look at this next example. Y equals x squared plus x minus 12. All right, so in this case, we should be able to factor this. So if we set up SPF, we need two numbers that sum to a +1 and add to a -12. So plus 4 minus 3 are going to be x plus 4, x minus 3. And then we can identify our zeros. I have x equals negative 4, x equals 3. So those are our zeros. So we could plot our zeros on the graph, 1, 2, 3, 4, and 1, 2, 3 for other 0, okay? But we need to be able to find our vertex too, so that we can make a complete parabola here. So remember, when we're trying to find our vertex, we're going to take the midpoint of our zeros. So the midpoint of our zero is going to be negative 4 plus 3 divided by 2, which is going to equal a negative 1/2. And then if we wanted to find the y value of our vertex, we're just going to go ahead and substitute that negative 1/2 back into my equation to find the y value. So a negative 1/2 plus 4 is going to be 3.5, and a negative 1/2 minus 3 is going to be a negative 3.5. So the y value of your vertex is going to be a negative 12.25. So your vertex is that x and y to make a complete coordinate. So your vertex is negative 0.5 and negative 12.25. So if I plot that point now in my graph, so I'm going to go negative half and down 12.25. It'll be somewhere in there. Okay, and then we can connect all those points to draw a nice parabola. Okay, so if we identify the number of zeros that we have in this graph, we can see that it crosses the x-axis at 2 points. We have 2 zeros. Again, I want to point out the degree and sign on your leading coefficient. So now we have a positive leading coefficient, right? We have a positive 1, and it's an even polynomial, right? It's a degree of 2 again. So that should tell us a positive even polynomial, like we saw in the last note. Our end behavior, both of them are going to be pointing up, which is what we see to be true here with this quadratic. One more thing I want to just point out, we were talking about the number of the turning points for linear. So if we looked at the number of turning points for our quadratic, we can see that both of them, on the quadratic in part B, the first one, we have a turning point that happens at our vertex. Our graph is increasing, 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 and then starts to decrease. On the second equation, our graph is decreasing all the way down to the vertex and then changes direction and starts to increase. So again, there's one turning point for both of those. So one turning point for quadratics, okay? 0 turning points for those lines. Okay, we'll take a look at some cubic and quartic nows, which are new equations that we just started talking about in the last note. So I'm going to pull up Desmos so that we can get an idea of what this graph is going to look like. Okay, so I've put the equation in Desmos. We can see that this cubic is going to start negative and then increase and then come back down and finally back up. So if I was going to draw this, just a rough drawing, doesn't have to be anything too accurate. I'm going to do something like this. All right, and we can tell by that our number of zeros. So how many times does it cross our x-axis? It's just going to cross our x-axis once, so we're going to have 1 0. I'd like you to pause the video and go ahead and try to factor the next one in order to identify where your zeros will be. Okay, so if you were to factor this, we should find that in factored form it's going to be y equals negative x times x plus 3 times x minus 3. And so I've identified my zeros as 0, and then a negative 3, and a positive 3. And we could graph this on Desmos, but I know it's going to look something like this. Okay, and just a couple things to point out about our cubics. First of all, we have a negative leading coefficient. And it's a degree that's odd, right? It's a degree of 3. So if we have a negative odd polynomial, it tells us that our endpoints are going to go up to the left and down to the right, which you can see is true of our graph. If we look at the first one we did, we have a positive leading coefficient, and it's a degree that's odd because it's a degree of 3. And so that tells us that our end behaviors are going to go down to the left and up to the right, which you can see is also true for this cubic. We did not point out the zeros on the second one, so let's do that. We have 1, 2, 3 zeros. The number of zeros is 3. Finally, let's talk about that number of turning points for cubics. So if we take a look at how many times the graph changes directions, for the cubic we can see that we go up, 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 and then we come back down. So we have a turning point there, and then we start to come back down, and then we go up again. So we have 2 turning points. We have a turning point here and here. And if we look at our other graph, we can see those turning points as well as those local maximums and local minimums. So our turning points for a cubic is 2. Okay, finally, let's look at a quartic. I'm going to go ahead and factor this. I'll pause the video while I do that and identify your zeros, and then we will put it on the graph. Okay, so if we were to go ahead and factor this, which is what we have here, you can see that we will get our zeros to be an x equals -2, 2, -1, and +1. So I've put those on my graph, and then we could put it in Desmo to see the general shape, but we're just doing a rough sketch right now. So I know it's going to come up and back down and up and back down like that. Okay, so the number of zeros for this, we have 1, 2, 3, 4 zeros. Okay, so keep that in mind as we're looking. This is a degree of 4, and we have 4 zeros. All right. Also, this is a negative, right? We have a negative leading coefficient, negative and even. If we have a negative even polynomial, that tells us that our endpoint should be going down, both of them, which looks to be true from the graph we just put on there. Okay, if we look at the next one, again, we'd have to put this in Desmos. If we were to put it in Desmos, I'll show you what that would look like. So there is that function in Desmos. We will just do a rough sketch of that on our graph on our note. So it looks like it's starting up high, coming down, coming back, down a little bit further, and then up again. Something like that. So I'm going to go ahead, pause the video for a minute, and get rid of Desmo so we can continue with our note. Okay, so with this graph, we can see that we don't have any zeros, right? It never crosses our x-axis, so we have no zeros. If we look again at the sign on this time we have a positive coefficient, and it's still an even degree polynomial because the highest degree is 4. So if we have a positive even, that tells us that both ends should point up, which is what it looks to be true from this equation. All right, and then finally, if we wanted to talk about the turning points, so turning points for quadratics, we can see that our turning points, hopefully we start to see a pattern here for turning points as they relate to the function. So we have 1, 2, 3 turning points where it changes from going decreasing to increasing or increasing to decreasing. And same is true here. I have 1, 2, 3 turning points. So 3 turning points for a quartic function. So let's summarize some of this in this chart below. From your observation above, complete the following chart. So our linear functions, we know that those are a degree of 1. And the minimum number of zeros, remember we had a horizontal line and we had no zeros. And our maximum number of zeros, we just had 1. With our quadratics remember are a degree of 2. The minimum number of zeros, again, if the polynomial was above the x-axis and going up, we would have 0, or if it was below the x-axis and pointed down, we would have 0 zeros. And then the maximum number of zeros we had was 2. Both endpoints kind of cross the x-axis. If we look at our cubic function on this page, we can see that in one graph, it's a degree of 3. In one of our graphs, we only got 1 0, so we would say that's the minimum number of zeros we could get. And the highest number of zeros we could get, we saw in the other graph, we got 3. Right? Our quartic is a degree of 4, And again, one of the graphs had a minimum number of zeros of 0, and the maximum number was 4. If we were to continue on, and keep in mind there's this relation between the end behavior and the zeros when we're talking about if the function is odd or even. So if we were to go on and look at a quintic polynomial function, which as you can imagine is a degree of 5, the minimum number of zeros for this would be 1, and the maximum would be 5. The next degree is a degree of 6. And again, if we had both endpoints pointing up or both pointing down, there's a possibility to have no zeros or up to 6 zeros. Okay, so we want to make a kind of a general statement for any degree polynomial function. So we're going to say an nth degree polynomial function. What are the minimum zeros? What are the maximum zeros? We know that the degree is just going to be whatever n is. And then the minimum number of zeros, you can see here that when we have an even degree, so when we had 2, 4, and 6, right? The minimum zeros we were going to have was 0. Okay, if we had an odd degree, the minimum number of zeros you could have is 1, other than my linear, right? My linear kind of stands on its own because it's a line. It doesn't have any turning points, so that one is kind of an outlier. So let's just summarize that. So if n is odd, then the minimum number you could have is going to be 1, other than linear. Okay, with linear we did see that we could have is minimum of 0. If n is even, then the minimum number of zeros you could have is 0. It could not cross the x-axis at all. How about the maximum? Let's make a comparison here. When we look at these, hopefully you see that the degree and the maximum number of zeros are exactly the same for all of them, right? If we had a quartic which had a degree of 4, the maximum number of zeros was 4, and that's true for all these relations. So we would say the maximum number of zeros is just whatever n is. So whatever n is. And then the only other point I wanted to make was about those turning points. So if we notice with the turning points, there was a relationship into how much turning points it actually had. If we look at this quartic, a quartic was a degree of 4 and it had 3 turning points. Okay, so we're always going to relate this back to the n value or the degree. A cubic function is a degree of 3 and it had 2 turning points. A quadratic had 1 turning point and a linear had 0 turning points. So hopefully you can see that we've created a pattern here. If we were going to go up to a degree of 5, that would have 4 turning points. A degree of 6 would have 5 turning points. So you can see that whatever n is, our turning points are going to be 1 less than that. So if we ever want to determine how many turning points a function would have, we would say that the number of turning points is just going to be n minus 1. All right, that's it for our notes for today.